Yeah, the second theorem that we are looking at is Norton's theorem. I'll be going through the PPTs only all through the session. Okay, so you can take time to copy that or listen to it very carefully and work it later on, because I'll be posting this soon after this session in YouTube link. This is very similar to your Thevenin's theorem that we have seen in the last class, and definition is also 90% same. Where the changes would be, okay? The Norton's theorem states that a linear two-terminal network can be replaced by an equivalent circuit consisting of a current IN in parallel with resistor RN. Okay, Thevenin's theorem, what was happening? Equivalent circuit consisting of a voltage VT in series with resistor RT, we used to say. So except that everything is same. See here, linear two-terminal network. There also in Thevenin's also you were handling the linear two-terminal network only. It is called as two-terminal because there are two terminals out like this AB. Understand that? So this linear two-terminal network, according to Norton's theorem, can be replaced by a current which is called as short circuit current or Norton's current, IN, short circuit current, in parallel with the Norton's resistor. Get this point, everybody? Okay. Norton says that any linear two-terminal network can be replaced by a current source in parallel with the resistor Rn. Understand? Whereas this in Thevenin's, it was a voltage source in series with the resistance, whereas it is in Norton's, it is current source in parallel with Rn. And how to find out this Rn? If the circuit consists of independent sources only, Rn can be found out by the deactivation of the independent sources or by turning off the independent sources. It is very similar to the resistance that we used to find in Thevenin's theorem. So let me give you the secret. The secret is the Norton's theorem and Thevenin's resistance are the same. The Norton's resistance and the Thevenin's resistance are the same. They are not different at all. Understand that they are not different. So the procedure that you used to follow your to follow you used to follow to find out RT is same to find out the resistance RN. See, Rn is the equivalent resistance at the terminals when the independent sources are turned off. Same used to happen there also in Thevenin's. We used to turn off the independent sources and find the equivalent resistance across the terminals AB. Similarly, we are doing the same here also. And IN is the short circuit current. We used to find out short circuit current, right? Where we used to find out short circuit current when we were doing that. So what is Norton's current? Norton's current is the short circuit current that flows through terminals A to B when they are shorted. What I mean is this. Suppose you short AB, okay? And the current that flows from A to B is called as short circuit current. That is your Norton's current. Understand? So this is your Norton's theorem, and very similar there also. If the circuit consists of the dependent sources, what you would do with the Norton's resistance, you would find Norton resistance as VOC by ISC. There also the Thevenin's resistance used to be find out as VOC by ISC only. Here also the same. There is no difference as far as the finding of the Thevenin's resistance and Norton's resistance are concerned. But in Norton's circuit, you will have the short circuit current in parallel with the resistance, whereas in Thevenin's circuit, you will have the voltage source in series with the resistance. Is that okay with you? So with that introduction to the Norton's theorem, let's see some problems. And before seeing the problems, how many types of problems there could be? There could be, as we have seen earlier, there could be two problems. One is finding out the Norton's equivalent circuit across the open circuit terminals. Another one is to find the voltage or current in the Norton's voltage or current in the circuit by Norton's theorem. So you need to be a little careful regarding what is asked in the problem. Are you finding out the Norton's equivalent network, or we are finding out current or voltage using the Norton's equivalent? Norton's theorem, sorry. So that needs to be taken care of. Let's see the problem now. So what is asked in the problem? If you can copy it down very fast. In this problem, they're asking us to find out the Norton's equivalent circuit across terminals AB. Okay. So it is finding out the Norton's equivalent circuit across terminals AB. That's it. It is not finding a voltage or a current using Norton's theorem. No, that is a different type of a problem. We have seen that when we were solving Thevenin's problems. Okay, very similar problems you'll have in Norton's. Very similar problems. Okay, so in this you'll be finding out the Norton's equivalent network across the terminals AB. So what is Norton's equivalent network? See, this is Norton's equivalent network. So they are asking us to find out the Norton's equivalent network across terminals AB means. So across terminals AB, we are supposed to find out the short circuit current and the Norton's resistance. So if you find out these two parameters, okay, so you have found out a Norton circuit. Now, how to find out ISC? See, in this problem, we need not have to find out VOC at all. VOC is not concerned here when the independent sources are involved. So we have to find out IC. How to find out ISC? See here, you need to short the terminals AB. You need to short the terminals AB, and this ISC would be flowing from A to B. And here is the ground. Why it has to flow from A to B only, you may ask. See, the ground point would be here, which we have not shown. Okay, so B is the ground point. Understand that? So the current would be flowing from this positive terminal to this ground terminal. So that is your ISC when we short AB. Okay, so steps to find the Norton's resistance. Very first, what we are doing is we are finding out the Norton's resistance. You can find out ISC or Norton's resistance. Anyone you can find out first. Step one, what is that? Turn off the independent sources. If the dependent sources are there, it's an entirely different ball game. Okay, since only independent sources are there, we can turn off them. What is that turning off the independent sources means? It's open circuiting the current source and short circuiting the voltage source. Is that okay with you? We have seen that earlier. Again and again, I'm telling you that open circuiting current source and short circuiting voltage source is what is the meaning of deactivating them or turning them off. Understand that? So let's do that. See here, this is open circuited. Why this is open circuited? See here, here is a current source, so this needs to be open circuited. Okay, and here is a voltage source, this needs to be short circuited. So after we open circuit this and short circuit the voltage source, so this is what I'm going to have. See, this is short circuited part, this is short circuited part, and this is open circuited part. Now after open circuiting you have these terminals, right? So this is of no use to me, and if it is there they may confuse you and may create problems. Okay, so just ignore them because they are of no use to me. Okay, so after ignoring them, okay, so the circuit would look like this. So what can we do now to find out Rn? Rn is the equivalent resistance that is there across the terminals AB. So what is Rn? How these 12 ohms and 4 ohms are connected? The 12 ohms and 4 ohms are connected in parallel. Okay, so that parallel combination is this: 12 into 4 divided by 12 plus 4, and that is 3 ohms. Understand that, everybody? Okay, so this is how we find out Rn. Okay, now once Rn is found out, what is the next parameter that we need to find out for Norton's circuit? We have to find out ISC. Steps to find the Norton's current. Short circuit. What is step one? What is step one? Short circuit the open circuit terminals and mark ISC action. See that you have done. Short circuit the open circuit terminals. AB are open circuit terminals. Understand? So we are short circuiting them. So after short circuiting, we are marking ISC like this. And what is that we do next? find the short circuit current by a suitable technique. They don't say you go with mesh analysis or you go with node analysis or you go with source transformation. No, they don't say anything. It is up to you, okay, to see which is feasible here. What is feasibility I'm saying? Okay, let's say which is suitable. Let's not say feasibility. Let's say suitable. What is which is suitable? Suitable technique is one which will give you the answer at the least time. Okay, suppose we approach this problem by mesh analysis. Everybody, suppose we approach this problem by mesh analysis. Okay, how many meshes are there? One, two, three. Three meshes are there. Okay, how many KVL problem it is going to be? Anyone, would you like to give me that analysis? Anyone, would you like to give me that analysis? How many KVL problem is this? Again, it is the same mesh analysis I'm saying. Anybody? Mushraf, you're there. 18 EC 51. Mushraf? No. Anybody who would like to come with that? Nobody? Okay. See here. This is 1, 2, 3, 3 mesh. But since there is a current source in between mesh 1 and mesh 2, so you form a super mesh between mesh 1 and mesh 2. How many unknowns would be there? This is current 1, current 2, current 3. 3 unknowns are there. So this is one KVL. This is another KVL. Okay. And we have two equations, but three unknowns. Another equation will get by constraint equation. So 3. So that is what your mesh analysis looks like. Fine. Now, what is your node analysis? How many KCL problem is this? How many nodes are there, first of all? How many nodes are there? How many nodes there? See here, this is just one node. It's all the same points. Get that? This is all the same point. So it is one node problem. So it is one KCL problem. So the node analysis is much better than the mesh analysis. Understand that? For this particular set. That's why they say suitable technique. So which technique is being used? Let's see. Which technique do you think is feasible? With the explanation that we have seen, the node analysis is what is feasible here. So by node analysis. So since it is terminal A, so we have marked the voltage as VA. Everybody is okay with that? Okay. So applying KCL at node A. Applying KCL at node A. So everybody do that yourselves now. Apply KCL, everybody. Go on applying. See, VA minus 24 by 4 is leaving. VA by 12 is leaving. ISC is leaving node A. The only entering current is 3 amperes. So sum of all the leaving currents is equal to sum of the entering current. Since there is just one entering current, let's keep it that way. Okay. Now, what is not good here? What is not good? What is not good means what is the intention? Intention is to find out ISC. Intention is to find out ISC. Okay. But we have two unknowns here. VA is also an unknown, ISC is also an unknown, and we have how many? We have how many equations? Just one equation. We have one equation, two unknowns. Just one equation, but two unknowns. How to deal with that? Anybody? Can you make out? How can we reduce this particular equation to one unknown equation? Two unknowns, one equation, not good. One unknown, one equation. Or if you have two unknowns, you should try having another equation. From where you will have? No, there is no possibility. Okay. So what you will do to find out the short circuit current here? Okay, let me give you. Do we know VA? Can you tell me what is VA by looking at this circuit? Anybody? Would you like to give me VA? by looking at the circuit. VA at node A, this node A is connected to ground. Okay, so what is this VA now? This VA is connected to ground. This voltage VA is connected to ground. What is ground? What is voltage at ground? It is 0 volts. So since this VA, this terminal A is connected to B, and since this B is connected to ground, it is as good as saying A is connected to ground. Since A is connected to ground, the voltage at node A is 0. So in that sense, VA is 0. That's why we can say there is one equation and two unknowns. Substituting VA equal to 0 in the above equation implies ISC is 9 amperes. Everybody's okay with that? So we have found out the Norton's equivalent circuit now across AB. So 3 ohms was what we had as Norton's resistance here. Okay, and ISC is what we have just got by substituting VA as 0. So wherever we short these two terminals to mark ISC, straight away understand the voltage at node A is 0. You're not supposed to forget this. Otherwise, you'll not be able to solve this problem. Most of them come here at this point and get stuck because it is one equation, two unknowns. But if you are smart enough to understand that A is connected to B and B is connected to ground, so voltage at A is VA, that would be 0. Okay, so if you understand that, you can find out ISC, otherwise no. So since we have found out the Norton's resistance and Norton's current, okay, we can write the Norton's equivalent circuit as this. So that is 9 amperes and 3 ohms. Is that okay with you, everybody? Fine. Let's move on to the next problem. So what is there in this problem now? What is being asked? See there, everybody. Find I naught in the network shown using Norton's theorem. You have to find I naught in the find I naught. Whereas in previous problem we were finding out the equivalent circuit. Here we are finding out I naught by using Norton's theorem. So what did we do in Thevenin's theorem problem? The same needs to be done. If you're asked to find out a voltage or a current, okay, so that you have to see which part of the circuit that is. So that needs to be removed. Understand that? So what is the solution? Step 1, separate the branch through which I naught is flowing. That means separate the branch where the I naught is flowing. Okay, find the Norton's equivalent network across the open circuit terminal. Soon after you separate this 2 kilo ohms, okay, you'll find open circuit terminals here. So across the open circuit terminals, you have to find your Norton's equivalent network. Is the second step. So then what is the third step? Connect back the separated resistor to find out I naught. Okay, so this is a three-step problem. First, separate the resistor. You will be availing the open circuit terminals. In open circuit, across the open circuit terminals, find the Norton's equivalent network. Okay, then once you have found out the Norton's equivalent network, bring back the resistor that you had separated, connect that back, and find out the current that is flowing through it. So that is what the solution would be. So step 1, separate the branch through which I naught is flowing. See, we are separating this. What way? So we have separated. So after separating, what is available here? You are availing two terminals here. See, two open circuit terminals, A, B. Name them A, B. Name them X, Y. Name them whatever you want. But we need to understand that there are two open circuit terminals. Understand that. So what needs to be done? We have to be finding out the Norton's. Again, this is like your first problem. From step 2 onwards, it is your first problem. What is step 1? Separation. Separation of the resistor is what you need to understand. Okay. Now, we have to find out, are you comfortable with terminals on the top? Are you comfortable, it is asking. Are you comfortable with terminals on the top? If not, you can tilt it. Okay, rotate it by 180 degree. 180 degree or 90 degree? 180 degree, yeah. Okay, do that, or you can just move ahead like this only. It's your comforts. Okay, if you're comfortable with this, fine, you can go on, mark your ISC here itself, or you can tilt it so that your terminals would become one below the other. Okay, like this. Your wish, again, your wish. Okay, absolutely no problem with whichever the way you want to look at your circuit. Okay, So to find Rn, what did we do to find Rn? Okay, across the open circuit terminals AB. So we are short circuiting the 12 volts. The only voltage, only source is voltage source. So we can deactivate that. How we can deactivate or we can turn off? How to turn off that? By short circuiting that. So we have short circuited. See here, here is where the network, the voltage was, that is short circuited now. Fine. So find out the Norton's resistance, everybody. How to find out the Norton's resistance here? It's not looking that easy. So you're not finding any resistor in series, any resistor in parallel. No resistor in series, no resistor in parallel. See, 6, 2. Oh, 6, 2 is in parallel. See here, 6 and 2 is in parallel. Yes, 6 and 2 is in parallel. Very sorry. Okay, 6k and 2k are in parallel, because see, this end is also short, the other two ends are also short circuit. So 6 and 2k are in parallel. So 6k 2k parallel. Okay, once that parallel combination is done, so that then you'll have the series combination. Okay, and this whole stuff would come in parallel again with this. So you can go step by step to see this. First, combine these two parallel combinations, combine. Okay, so you will have the whole of this part would be replaced by the parallel combination. Understand that? Then that parallel combination would be in series with this, and this whole stuff would be in parallel with 4k. So that is how we have obtained this to be 2.12 kilo ohm, so that you can do step by step and look at that. Fine. So if you are still not comfortable, what you can do, you can catch hold of the star. 6, 2 and 3 is there, right? You can catch hold of the star and convert that into a delta. The things may become simple. The things may become simple and would become simple. Yes, why may? Okay. So if you are not good enough with this, you can go convert this star. 6k, 3k, 2k is there. You can convert this star into delta and see, you should get this. Fine. So after finding out the Norton's resistance, we have to find out the Norton's current. So how to find out Norton's current? The open circuit terminals are short circuited, and the current that flows from A to B is your short circuit current. So mesh analysis or node analysis would again be a question. Let's go by mesh analysis, because you have three meshes, three mesh equations. If you go by node analysis, how many nodes are there? You have 1, 2, 3. 1, 2, 3 nodes. So this would be a super node problem. So if you want to approach this by node analysis, okay, by all means you can do that. Fine. Yeah, what is the voltage here? This voltage would be 0, because here you have to be marking ground. Understand that this voltage would be 0. Okay, so this is how the things go. You can approach this by node analysis or mesh analysis. I'm going by mesh analysis. So in mesh analysis, we have to marking the three currents. Okay, KVL to mesh 1 is this, looks like this. You can just see that. Again, I'm not explaining you KVL. Sorry, yeah, KVL. See here, 4k into I1, 2k into I1 minus I2, plus 3k into I1 minus I3 equal to 0. Okay, bring that into standard form. Then KVL to mesh 2. Okay, minus 12, because I'm approaching minus sign, plus 6k into I2 minus I3 plus 2k into I2 minus I1. Bring that to the standard form. So this is all something that you can do yourselves. So I'm rushing through because we are lagging in time. Okay. Then the third equation can be obtained by applying mesh KVL to what? Mesh 3. So what is it? 3k into I3 minus I1 plus 6k into I3 minus I2. You're not supposed to bring ISC there, because ISC is the current and we are writing the voltage equation. So ISC has no place in KVL. Whereas in KCL, it had the place. But when there is no ISC involved in all the three, how can we find out ISC? What is ISC? ISC is actually your I3. See here? I3 is moving from A to B in this particular mesh. So this is your ISC. Understand? Three equations, three unknowns. Find all the three unknowns. Okay, and what is your ISC? ISC is I3, as I explained you here. Fine. So we have 5 milliamperes and 2.12 kilo ohm as the Norton's resistance. So this is how our Norton's equivalent network looks like. But this is the problem does not end here, because we are asked to find out what? What is that we are asked to find? We are asked to find out I naught. Let's not forget that. Let me go back and show you. See, we are asked to find out I naught. We had separated this 2 kilo ohms, mind you. So this needs to be found out. In step 2, we have just found out the Norton's circuit. What next? What next? So we have to reconnect the 2 kilo ohm that we had separated. And I naught is the current that they showed us moving from A to B. How did you mark this as A to B? Because very clearly it is shown here in the circuit. See, this is where our A is, this is where our B is. A, B. So this is where it is flowing. Okay, so A to B is where you have to mark your I naught. Okay, so that is marked here and connected. So find out I naught. How can we find out I naught? You can go by mesh analysis, node analysis, or there is another technique. See, there are two resistors in parallel and there is current entering this. Okay, so by current division rule, we have found out mesh analysis, node analysis, or something else. So we can go with current division method. So by current division method, I naught is equal to total current into resistance of other branch divided by sum of the resistance. So that is what the equation is, and we get our I naught to be this. Is that understood? Let's move on with the next problem. So how is this problem? It is involving, how is this different? It is involving a dependent source. So when the dependent source is involved, Rn has to be found out as VOC by ISC. Understand that? So is this the circuit complete? Is this circuit complete? They're asking. Can anybody answer? Is this circuit complete? Just for curiosity's sake, the question is this circuit complete? No, there is a dependent voltage source involved which depends on the current IA. Unless that current IA is given in the circuit, okay, so this circuit is incomplete. So what needs to be given? See, this IA needs to be given. Understand that, which is flowing here. This need not flow here. That they have told that this is flowing here. That's why we are taking it through 1 kilo. It is not we who give this IA. It comes in the equation itself. Okay, this is complete now. So for finding out the Norton's equivalent network, we have to find out ISC and RN. Since the dependent sources are involved, RN has to be found out as VOC by ISC. That is what is the catch here. Okay, it's not only ISC that we need to find out. We have to find out VOC also, because the Norton's because this problem is involving the dependent source, and dependent source cannot be deactivated. So let's find out ISC first. So what is that they're doing? They have marked VA, means they're following node analysis. And what is VA? Let's see what is VA. VA is 0. You should understand. Though I'm marking VA, VA would be 0 in the equation that we write. Okay, let's see that later. But just VA is 0. Since VA is 0, what is IA? IA is VA by 1K, right? Since VA is 0, VA by 1K would also be 0. So IA is also 0, VA is also 0. Now see here, VA is 0, fine. Since IA is 0, what would this be? Since IA is 0, what would this voltage source be? This voltage source would be a short circuit. Okay, so this is short circuit and IA is 0. Hence the circuit becomes this. Understand that? The circuit becomes this. So find out your ISC, simple. So KVL you apply and find out ISC. I is ISC now. 2 milliamperes. We have to find out VOC also. So mark VOC across the open circuit terminals. Now this is your VOC. Now this VOC is not 0 because A and B are not short circuit, right? So this VOC you cannot say 0. So this is open circuit voltage. So KCL at node A. Okay. So how is this? This is VOC plus 2000 IA minus 12 divided by 6K is the current that is leaving this. So I have explained, we have solved such problems in node analysis. VOC minus of minus this divided by 6K is the current leaving. The current leaving here is VOC by 1K, and no entering current, so it is 0. Understand that? So IA is there. So in this equation, we are finding out VOC, right? So try express IA in terms of VOC. What is IA in terms of VOC? IA in terms of VOC is VOC by 1K. Okay, IAC is VOC by 1K, and after you do that, okay, we get VOC to 4 by 3. So we have found out ISC and we have found out VOC. So once we have VOC and ISC, what do we have with us? We have our RN. Understand this point? So RN is VOC by ISC, and that is 667 ohms. RN is understood. So VOC is also there, ISC is also there. So the Norton's equivalent network is this. So unknowingly, we have found out something else also. Unknowingly, we have found something else also. What is that we have found out? See here, RN they say, right? And I've told you RN is RT only. The Thevenin's resistance and Norton's resistance are the same. Understand that? So we have found out RN means it is as good as finding out Thevenin's resistance. And since you have VOC here, this VOC itself is your VT. So in a by doing this, we also have found out the Thevenin's equivalent network. Everybody understand that? So we have found out Thevenin's equivalent circuit also. What is the summary now? So Norton's equivalent network across the closed terminal is ISC in parallel with RN. If the circuit consists of the independent sources, RN can be found out by deactivating the sources. Okay. For deactivation of the sources, replace the voltage source by short circuit and current source by open circuit. Okay. If the circuit consists of the dependent sources, find RN by using VOC by ISC. If the Norton current is transformed, we get a Thevenin's voltage source. So this is important. What is important? So if you transform, what is source transformation possible? Yes, because there is a current source in parallel with the resistor. If you transform this, you will get a circuit, and that circuit would be the Thevenin's circuit. Understand? By source transformation, we can get Thevenin's from Norton's, or from Thevenin's we can get Norton's, and from Norton's we can get Thevenin's. Understand that?